Welcome to lecture 24. So, in this lecture we will be looking into static and dynamic RAM. So, broadly these are the two semiconductor memory system, two types of semiconductor memory system that we will be seeing, and we will be seeing that how a single bit SRAM or DRAM chip is built, how a single bit is built, and then you can extend it to any bit. So, as I said, broadly two types of semiconductor memory systems exist: static random access memory and dynamic random access memory. Under dynamic random access memory, we have two more types. One is called asynchronous DRAM, another is called synchronous DRAM. Now, how these types of semiconductor memory vary? So, how you can differentiate among them? They vary in terms of speed, that means how fast it is. How fast is your SRAM or how fast is your DRAM? In terms of density, that means within a same area, how much bit you can pack using SRAM or how much bit you can pack using DRAM, that is meant by density. Volatility, by this volatility property we mean that whether the data will be, how much time the data will be retained. So, if you have power supply given to it, then static RAM will have its data, but in case of dynamic RAM, even if you have supplied the power, the data will not retain. You have to do periodic refresh to get the data. So, these memories vary in terms of speed, access time, density, the volume of data that can be put in a same area, volatility property, and the cost. So, cost is also very important. So, we will see that all these things are very much related to each other. So, we will be seeing that if you want to have a very high speed thing, you have to pay a cost for that. If you want a very voluminous thing, then you cannot afford to have a high speed. So, we will see the pros and cons of these properties. So, present day our main memory system are built using DRAM and cache memory systems are built using SRAM. And we will see that our cache memory system is relatively fast, but it is small, and our DRAM is relatively slower, but it can store a large amount of data. Coming to static random access memory, SRAM. So, SRAM consists of circuits which can store the data as long as power is applied. I have already told this. In this type, a semiconductor memory, what it uses? It uses a bistable latching circuitry, that is a flip-flop, to store each bit of data. So, store individual bit of data, a bistable latching circuitry is used, that is flip-flop, for storing. And SRAM memory arrays can be arranged in rows and columns. So, we have already seen that how a memory cell is organized. A memory cell is organized as in terms of rows and columns. So, in the rows and columns you have one bit of data. So, by this what we mean that this is also SRAM memory is also arranged in terms of rows and columns. So, we hit a row and then we get the data from every column depending on the word size. So, SRAM memory arrays can be arranged in rows and columns, just now which I have said, and these are called word line and bit line. And we have also seen what is a word line and what is a bit line. Now, SRAM technology can be built using 4 or 6 MOS transistors. So, we can use either 4 or 6 MOS transistors, but modern SRAM chips in the market, it uses 6 transistor implementation for Cmos compatibility. And this kind of SRAM chip which uses 6 transistor are widely used in small scale systems like microcontrollers and embedded system. We know that today's day microcontrollers and embedded systems are everywhere. So, and it does not require very large memory. So, this SRAM chip, but it requires faster memory. So, SRAM chips are used in these microcontrollers and embedded systems, and also used to implement cache memory in the computer system, which will be discussed later. Now, before going to this slide, I will just discuss two things. One is PMOS transistor, another is NMOS transistor. So, in this PMOS transistor, you can see that there is an input, that is X, and this is source or drain. This is the transistor. Basically, this input acts as a switch. This transistor acts as a switch, and this is controlled by this input. If this X input is 0 for PMOS transistor, there is a conducting path from S to D. So, T1 is on. If X is 0, then there is a conducting path from S to D, and this will make T1 on. This transistor T1 will be on. This is the feature of PMOS transistor. Now, see the NMOS transistor. In NMOS transistor, in the same way, if this value is 1, then only there is a conducting path from S to D. So, what is the difference between these two? In PMOS, if the input of this is 0, then only it will be conducting, this switch can be made on, and in NMOS, if this input is 1, then only this transistor will be on, that is, there will be a conducting path from S to D. So, we need to know these two PMOS and NMOS transistor, because these transistors are used to build your memory chip. Now, come to a 1-bit SRAM cell, how it looks like. Here, so this is a single bit SRAM cell. Here, two inverters, this is a symbol of inverter, this is a symbol of inverter. So, two inverters are cross connected to form a latch. So, if you give a 0 input here, this will be 1. If you give a 1 input here, this will be 0. So, two inverters are cross connected to form a latch. And now, this latch is now connected to two transistor T1 and T2. Now, what is T1 and T2? You see, this is a NMOS transistor. So, this kind of transistor is used here. So, if you want to activate this transistor, what input you have to give? You have to give a 1 input here, then only this transistor will be on. So, this particular latch is connected to the 2-bit lines. If you recall our discussion, each of the cell is connected to 2-bit lines B and B bar. In the same way, this is a cell, this is a single cell which is connected to 2 bit lines B and B bar through this transistor T1 and T2, and these transistors behave like switches. So, if switches means a switch can be made on, a switch can be made off. If you want to make this transistor on, so that meaning if you want to make this switch T1 switches on, then you have to activate these lines. You have to give a 1 input here, then only this T1 transistor will be on, that is closed, and if you give a 0 input, it will be off, that is it will be opened. And to retain the state of the latch, the word line can be grounded, which makes the transistor off. Now, if I want to retain the value what is there in the latch, in that case what we have to do? We have to give this word line to ground. If it is ground, this will be 0, then there is no conducting path. Whatever value is in the latch, it will remain there. Okay. So, we have bit lines, 2 inverters are cross connected to form a latch, and these are connected to 2 transistors through to the bit lines through this transistor, and this transistor can be made on and off. Depending on that, we can read the value or we can write the value into this cell. Let us see that. Read operation. How we will read the value? That means, if the value here is, let us say 1, then 1 will be at this A and 0 will be at this B, because the bit line will have 1 and B bar, that is the complement, will have 0. To read the content of the cell, what we need to do? The word line is activated. So, now I want to read this content whatever is in A and B. So, we need to activate this word line. By activating means we are supplying 1 here. So, if we make it on, if we activate this word line, then what will happen? This transistor T1 and this transistor T2 will be on. If this transistor T1 and T2 is on, then the value which is stored in A and B, that is in the latch, will be available on bit line B and will be available on bit line B bar. So, whatever value, if the value is 1, then 1 will be available in the bit line B and 0 will be available in bit line B bar. In the same way, if the value is 0, then 0 will be available in bit line B and 1 will be available in bit line B bar. And then a sense or write circuit connected to the bit lines will monitor the state of B and B bar, and accordingly it will see that, it will figure out whether it is 1 or whether it is 0. So, this is how we perform read operation here. So, what we do, I will just repeat once more. We activate the word line. Activating the word line, this transistor T1 and T2 will be on. Whatever data will be in A will be available in B. Whatever data is in B will be available in B bar. And similarly, a sense or write circuit which is connected here will sense the value, and accordingly it will transfer it to the data lines. Now, moving on, let us see the write operation in SRAM. Now, for writing, we can either write 1 or we can either write 0. First, see if I want to write 1. If I want to write 1, then what I need to do? I need to set 1 in bit line B. In this B, I have to set 1 and I have to set 0 in bit line B bar. So, bit line B will have 1, bit line B bar will have 0. Then I will activate the word line, which will make the transistor T1 and T2 on. Whatever value is in the bit line will be available in A and whatever value is in B bar will be available in B. So, the data is written to the latch. Similarly, if I have to write 0, then I apply 0 in the bit line B and 1 in bit line B bar, and in the same way I activate the word line. By activating the word line, the transistor will be on, and whatever data will be in B will be stored in this latch, and whatever will be in the B bar will come here. So, this latch will now have the value which is there in this bit lines will be available in this latch. And now, as I said, I can either write 0 or I can write 1. The required signals, that is either 0 or 1, will be generated by the sense or write circuit. So, this is how write operation happens in SRAM. Now, see, before moving here, if you consider this diagram, you have a NOT gate. So, let us see the CMOS realization of NOT gate. Here is the CMOS realization of NOT gate. So, you can see here that this is the circuit. A PMOS transistor. A PMOS transistor is connected here. This is T1, and an NMOS transistor is connected here, which is T2. Now, this is a NOT gate. Let us see how this will act as a NOT gate. NOT gate means if I give X input as 1, the output should be, if I give X input as 1, the output should be 0. Let us see if I give X as 1. If I give X as 1, then the above transistor, this is T1, will not be conducting, because this is a PMOS transistor and it will only conduct when the input here is 0. So, there will be no connection from this, this is not connected, this is closed, this is open, T1 is off. Now, if this is 1, this transistor, the bottom transistor, that is T2, which is a NMOS transistor, will be on, and there is a path from this Y to ground. So, if there is a path from this Y to ground, then this Y will have the value approximately equals to 0. So, when this X equals to 1, T1 is off, this transistor is off, and T2 is on, this transistor is on. Hence, Y will be have approximately a value of 0 volt, which is equivalent to 0. Now, let us take X as 0. If X is 0, I must get the output as 1. Let us see whether we will get it or not. If this is 0, then the above transistor, that is T1, will be conducting, but the below transistor, that is T2, will not be conducting. If this is conducting, there is a path from this 5 volt to Y. So, this Y will have roughly equivalent to 5 volt, which is equivalent to 1. So, if we give input 0, the transistor T1 will be conducting and we will have an output 1, and if X is 1, then the below transistor will be conducting and we will have the output Y. Now, what we will do, once I have shown you this CMOS realization of NOT gate, now moving on, we will see 6 transistors static RAM cell. Now, see this 6 transistor static RAM cell. This is the CMOS realization of NOT gate. So, I have just replaced this NOT gate and this NOT gate with the CMOS realization of the NOT gate. And now, what we are getting? We are naming these various transistors. So, this is transistor T1 and T2, initially it was there. Now, this transistor is T3 and T5, and this transistor is T4 and T6. So, we have just placed what I have just shown you, the 2 NOT gates, realization of 2 NOT gates here to form the latch. Now, 1 bit SRAM cell with 6 transistors are used in modern day SRAM implementation. So, this is the kind of cell that are used in modern day implementation. So, you can see T3 and T5 and T4 and T6 forms the Cmos inverter that I have just now explained, and reading a data, the data that is to be read or written can be done in the same way as explained in the previous example. Now, let us see in state 0 what happens. In state 0, that means this x is having 0 and this y is having 1. In state 0, the voltage at x is low, so here it will be low, and the voltage at y is high. X is low, so x input is going to this T6 and it is going to this T4. So, if it is going to this T6 and this is 0, then this will be off, but this T4 will be on. And now, y input is having 1. So, if this is 1, then this T5 will be on, but this T3 will be off. So, that is what T4 and T5, T4 and T5 will be on, while T3 and T6 will be off. Now, when the word line is activated, T1 and T2 are turned on. So, these are turned on, and the bit lines B and B will have what value? It will have a 0 value, because here see this transistor will make, as this is conducting, whatever is here it will bring down to ground. So, it will be equivalent to 0, and as this is conducting, this will be equivalent to 5 volts say. So, this will make it 1. So, this is how in state 1 it happens. Similarly, state 0, it happens like this. Now, let us move on. What happens in state 1? State 1 means x will now be high and y will be 0. That means, the bit line B should have 1 and B bar will be 0. So, as x is at 1, so x is going here and here. So, this will be off, but this will be conducting. And similarly, y is 0. So, y is low or 0. So, this will make this as non-conducting, but this will be conducting. So, T3 and T6 will be conducting and T4 and T5 will be off. Now, when the word line is activated in the similar fashion, T1 and T2 will be on, will be turned on, and the bit lines B will have 1 and bit line B bar will have 0. So, this is how what happens in state 1. Let us see some features of SRAM. So, here the current flows in the cells only when the cell is accessed. This is a Cmos cell property. So, current flows in the cells only when the cell is accessed. Because of this latch operation, power consumption is little higher. What is the simplicity? No refresh circuitry is required. It is of course volatile, but as long as the power is supplied to it, you need not have to do any kind of refresh. It is much faster. So, access time is very fast. So, the fast memories like cache are built using these kind of cells, but the cost is high. Why? We see that here we require 6 transistors to build 1 bit. Also, the space it takes is also more. So, it is the cost is high. and of course, it has got limited capacity, because we cannot build a very large SRAM cell, as it requires 6 transistors per cell. Next, coming to dynamic random access memory. In dynamic random access memory, as we know that it do not retain the state even if power is supplied to it. So, here the data are stored in the form of charge on the capacitor, and this charge tends to this charge cannot be stored for longer period of time, and this happens due to some leakage property of the capacitor as well as this transistor. But you see how simple is the cell. You have one transistor which is connected to the bit line, and this transistor is also connected to the word line, because through word line it will get activated, and the transistor is also connected to this capacitor which is grounded, and then it is connected to the sense or write circuit. This is a one transistor DRAM cell, but it requires periodic refresh, because we are storing the data as charge in the capacitor, and this charge can be retained not for longer period of time. These are less expensive, we can see that, because only one transistor is required to build it, one transistor and one capacitor is required to build this, and here the address lines are multiplexed. We will be seeing this little later. Now, let us see how we can read the value here. So, as we said that the data is stored as a charge is stored in this capacitor, and that represent whether a value bit 1 is stored or bit 0 is stored. So, let us say for reading the data from this cell, the transistor of this particular cell is turned on by activating the word line. So, this is the word line. We activate the word line such that this particular transistor T is on. Now, we have a sense amplifier connected to the bit line, and this line, it senses the charge stored in the capacitor. Once this is on, there is a connection between this bit line to this through this transistor. If the charge is above certain threshold, then we say that the bit is maintained at high voltage, that is 1, and it will represent logic 1. Similarly, if the charge is below certain threshold, then we say that the bit line is grounded, which represent a logic 0. Now, we see that if we read a cell, automatically it is getting refreshed, because we are keeping required data that is to be stored in this capacitor. So, if it is 1, then this is made on and we sense the charge in the capacitor, which automatically refreshes it. In the same way, if 0 is there, this also automatically refreshes this. In the write operation, what happens? Through this sense or write circuit, this bit line will have the available data, either 0 or 1. The transistor of this particular cell is turned on by activating the word line, and depending on the value that is to be written, either you have to write 0 or 1, an appropriate voltage is applied to this bit line. And as an appropriate voltage is applied to this bit line, this capacitor gets charged to the required voltage. If it is 0, a required voltage, it is charged to that required voltage. If it is 1, it is charged to that particular required voltage. And refreshing of the capacitor requires periodic read write cycles every few milliseconds. So, in every few milliseconds, even if you are not reading, you have to do refreshing to store the data, to keep the data. Now, there are various kinds of dynamic RAM. One is asynchronous DRAM, another is synchronous DRAM. As the name suggests, in asynchronous DRAM, the timing of the memory device is handled asynchronously. What do you mean by that? Here, there is no timing, no fixed timing, that when you read, when you given a request for read, when the data will be available. This is the processor has to take care of that when the data is available. But in case of synchronous DRAM, it is not like that. There is a timing involved to it, and after that particular time, the data will be available. So, here in asynchronous DRAM, a special memory controller circuit generates the signal asynchronously, and the DRAM chips that are produced between early 1970s to mid 1990s, they all used asynchronous DRAM. But today's day computer all uses synchronous DRAM. So, here the memory operations are synchronized by a clock, it is synchronous. So, a clock is there which synchronizes it, and this concept was already available in the 70s, but commercially it was available in 1993, and by 2000 SDRAM was replaced almost all types of DRAM in the market. So, there is no asynchronous DRAM these days, we have all synchronous DRAM, and the performance of SDRAM, synchronous DRAM, is much higher compared to all other existing DRAM. So, we have seen in this lecture what are the semiconductor technologies that are used to build SRAM and DRAM, what are the various kinds of DRAM exist, and now we will be seeing specifically the various kinds of DRAM. Thank you.